A CD, which is short not for compact disc, well, it is short for compact disc, but it's also short for certificate of deposit, is something where you could go to a bank and purchase one of these for a period of time. And again, it's an alternative form of interest. So instead of investing in the government or in a corporation, you could invest in basically a bank by giving them money, and then after a later point in time, they'll pay you back plus interest, which typically certificate of deposits are using compound interest instead. Again, it can really depend. So I'm just kind of making up some examples here, but just to sort of illustrate the differences behind the math, if it were compounded versus if it weren't. And what we're going to do is we're going to use the exact same numbers from the previous example and just look at, well, what if this CD is compounded annually instead of using simple interest? What's the difference in the growth of this account over time instead? So let's say you go into the bank and you purchase a $10,000 CD for 4 years with a 3% interest rate, all the same parameters as before. But let's assume that it is now compounded annually. What is the difference and what will happen? But basically, instead of just growing by a raw 12%, which is, the kind of the idea, right? 4 years, 3%, 12%. It's going to grow by a little bit more than that due to the compounding. And again, we could start with the formula to try to get a grasp on how this will all behave. But basically, for compound interest, the future value is equal to the principal times 1 plus the interest rate over the number of times compounded, raised to the nt power. So I'm going to start by just copying down the formula, and then we will make sure to try to plug in everything into that afterwards. So 1 plus r divided by n to the nt power. Okay, so in this case, we need to figure out, if we're trying to find the future value, what is everything else? So the principal, still $10,000. And in all the formulas, that's kind of how it's going to work. What are we starting at? And then notice the structure is then I'm multiplying by something. Here, I took the principal and I multiplied by this. Here, I'm multiplying by sort of a different thing. And that's really the only difference when we're compounding it. But I'm going to take 1 plus the interest rate, which still must be plugged in as a decimal, 0.03. That's all divided by n. And just to review what n means, because I haven't talked too much about that, n stands for the number of times that it will be compounded each year, which just means, well, how many times are we applying that percentage in a year, which in this case, again, this is something you'll need to know because it will depend, but it says compounded annually, which just means once per year. So n is going to be 1 here because, it's only going to happen, and usually this would be January 1st. For typical financial transactions. But basically, n is going to be 1 because it says it's compounded annually. And so that's also raised to the power n times t. An important thing to note about this formula is that the order of operations imply that we need to do the if you're following PEMDAS and stuff, people often go down the wrong road about what's supposed to happen here. But the fact that n and t are both in the exponent, that needs to happen first. So if I'm looking at this product of 1 times 3, this whole thing should be raised to the 3 power, not the 1, then the 3 power. They're not like stacked separately, but actually technically that does work. But essentially what I would recommend doing is calculate this product first, which sometimes this is referred to as capital N, the number of total pay periods, which we'll see in the next example how that changes. But in this case, if we do a little bit of this math, we're going to have 10,000 times 1 plus 0.03, which is just 1.03, and dividing it by 1 doesn't do anything, and then raising it to the 3 times 1 power is just 3. So notice this is very similar to the example from the first video. I'm just going to take my principal and I'm going to multiply by 1.03 every year. So over 4 years, whoops, sorry, t should be 4, not 3, so I made a boo-boo. There we go. Basically, every year it's going to grow by 3%. And in each successive year, it's gonna also grow by the new value. So again, if I thought about it on a year-by-year basis, I'm gonna start with 10,000. First year, my balance will be this, The next year, my 3% will be applied to the current balance because it's compounded, so it's a little bit more. And then over the course of 4 years, it's going to amount to this much, which, as I can tell from what I just did, is exactly this, right? 10,000 times 1.03 times 1.03 times 1.03 times 1.03, hence being an exponential growth, which gives it that shape. But anyways, that approximates to about 11,255.09. And, with finance, we round our answers to the nearest cent because there's no digit in money smaller than the penny. So you can always just round to the nearest hundredth. You don't have to worry about rounding any differently, especially if it's not specifically stated. But anyways, this would give us the balance of our CD when it's finished. And basically, one of the other things I want to do is compare to if it was just simple interest, this would be our future value. But if it is compounded yearly, it's actually going to be a little bit more. And that's kind of the difference, that the graph is illustrating, is that over time, compound interest will always grow faster than simple interest. And this is another general principle, is the more times it's compounded, the faster it will grow. So if you're comparing types of interest, if you're borrowing money, you typically want it to grow slower. But if you're investing, so like in this case, we'd obviously rather have more money. So compound interest is favorable to us as the lender. But let's say we're borrowing money and kind of flipping the situation here. Let's say I borrowed $10,000 and then I have to pay back that amount later. As the borrower, I'd prefer simple interest because it's growing slower. I'd rather pay this back than this back if this is something I owe. So it's important to notice the difference between what's favorable to who. But really, I think it's simpler just to remember that simple interest is the slowest type. Compounding is always faster. And if we compound more frequently, it will only speed up the growth of the account, which we'll see in the next video.